Greetings 2021ers, this is Professor Kaufman, and this video will serve to overview Project 5, which is the last project that we'll have for the semester. It's a short but sweet foray into the fine art of memory allocation. Through the course we have been coding in C, and you'll have made use of the functions malloc and free, and it is high time we look inside these just ever so briefly to have a gander at what those functions look like on the inside. And so during the course of this project, you'll be implementing a memory allocator. You'll come up with your own versions of malloc and free, referred to as lmalloc and lfree. The L there is short for explicit list and relates to one of the underlying data structures that will show up. It is a linked list that's used to track those pieces of memory that are available to be doled out and those that are in use at the moment and so shouldn't be doled out by calls to lmalloc. So as usual, the project specification has a number of items in it. That includes a code pack up top that you want to download and get to work on, a little manifest of what you can expect to find in there. This includes a skeleton code in lmalloc.c. It's the only code that you are required to complete. Some of the functions in there are already provided, but those that you need to implement are marked as required in capital letters, so search around there. There's also a demo program I guess this should be a demo.c rather than .h. I'll fix that later on. But the results of that demo then are used both in testing, and we can look at it down below later in a moment to see what's happening there. At any rate, there's some small treatise on what mallocs do and so forth, but I'd like to fast forward to the middle of the spec. Oftentimes stories are most interesting when you begin in the middle, by having a look at one of these sort of global diagrams that's provided. And as you would scroll through this, you'll find a number of colorful diagrams that are useful in understanding parts of the project. The one I'll start with is here, in that any memory allocation system that would allow for allocation and deallocation and reuse of memory is going to have certain features to it. They first need some sort of global store of memory to manage, and that's shown here as this big block of contiguous memory up top. Now, a first question that you might ask is, where does this thing come from? And we already have some answers to that based on our lecture discussion. This can be memory mapped. This is a request directly to the operating system to map some space into the virtual memory image of the program that's running. We'll get to how that looks in a minute. It pertains to the last part of the project, which has you expanding the space. But for the moment, you can just assume there's a chunk of memory that's been given by the operating system. It's independent of the malloc and free system that you tend to use in C, and instead comes from a sort of higher authority there. And then we're free to make use of this big chunk in whatever way you want. And in our case, we'll be implementing this malloc and free business so that certain chunks of the memory are in use at any given time, and pointers from other parts of the user program, like from the stack or other parts of the heap, will refer into these gray blocks that are in use at the moment, versus other little chunks haven't yet been doled out as a result of a malloc, or perhaps they were doled out earlier and free was called on them. They're marked in yellow as available. And the little key down here gives you some indication of that. In order to keep track of what is available and what is in use, there's some bookkeeping information that any sort of memory allocator needs to make use of. And a common strategy is to overlay some linked list in here to keep track of those things at least that are available. And since this is a student implementation and we want to make it easier to debug, we'll also keep a linked list of those blocks of memory that are in use at any point. So you can see some of the linked list stuff that's overlaid on the top here. And there are some global control structures that are housed in a struct called lcontrol. This is a global variable, and it has some lists available to it, along with some other fields that, for instance, bound the heap to say this is the first memory address that's valid in the heap, this is the last memory address that's valid in the heap. If you were to search through to find an available chunk of memory, then you'd start the search down here in the available list, which currently has 3 blocks in it. Now, I'll be using this term block quite a bit, and by it I mean this little chunk that's the yellow part plus the 2 parts that are adjacent that I'll refer to as a header and a footer. We'll get to why we need both a header and a footer later. But for now, one of the things that you should know is contained in this header and footer are some linked list pointers. So that allows me to start in this global variable that says this is the beginning of the available list. If I chase that pointer, it'll take me directly to the first yellow block. And if I don't like what I see there, for instance, if I'm looking for 50 bytes, because someone wants 50 bytes to use, they're called Malloc or Malloc in our case for this, you find there's some stats here that say, oh, there's only 22 bytes available here. So I'm going to bypass that. Go to the following link in this, the next link, and see this one only has 16 in it. Chase that link and find, this block actually has 100 bytes in it. So this would be big enough to satisfy a request for 50 bytes. And with a little bit of work, I might take this yellow stuff, gray it out, so therefore take it out of this available list and put it into the list of used blocks. If for some reason I wanted to traverse those, I could similarly follow a beginning link over here to find this one is in use. That's designated here by the little U that's in the header part of this struct, versus the A indicating that's available. And then chase links along here to see this is in use, this is in use, chase this link, this is in use, and this is in use as well. What you should notice from a global diagram like this is that the linked lists themselves, they don't pertain to any ordering of blocks in the heap over here. Instead, you jump quite around. You may go from a later block to an earlier block as you chase links in the available or used list. And generally, anytime you would say, oh, I'm going to take this out of the available list and put it into the used list, the convention is going to be to put it at the front of the list that you're inserting to. What should also be apparent then is that the heap is a little fragmented here. There's some available pieces. So I've got 22 bytes available here, 16 here, 100 here. That's a total of 100 and I think 38 bytes. So the 100 here plus 16 plus 22, 138 bytes. But importantly, if someone asked for 138 bytes, I couldn't provide it because that space is scattered around. And since there are a bunch of user pointers to stuff that's in the heap right now, I can't rearrange this willy-nilly. Instead, that would validate these pointers over here, so you're sort of stuck at that point. At the juncture that someone might want 138 bytes, then you'd usually, in this case, have to expand the heap to create another contiguous hunk that's over here, but that has enough space for further allocations. We'll get to that a little bit later on. But this is generally then the scheme that folks oftentimes use and is present in the glibc version of Malloc and Free that you've been using up to now, that at least part of the heap is managed through linked lists like this. And as things get allocated, they move from available to free. And as they get deallocated, they will move from the in-use list back into the available list. And later on, we'll talk a little bit about if you have two available chunks, it doesn't make any sense to keep them as separate. You can merge them into a single available chunk. First, though, just a few details about these blocks and the headers and the footers that are associated with them. This pertains to the early part of the spec, and down here is a somewhat more detailed diagram of what a header and a footer look like. These are just C structs, and so the blue part here, which is the header, has 4 parts. There's how big the space allocated in this little region here might be. There's a character that represents the state, which will be either used or available, represented by the L available or L used symbols. And then a couple pointers to the previous and next blocks that are in this list. And importantly, while the figure here shows things sort of immediately to the left or immediately to the right, as we saw on our global diagram, these pointers might actually point way off into another part of the heap because they're supposed to refer to other folks that in this case are in the used list, the set of blocks that are in use by the user right now. Now eventually when you create one of these, a user is going to get a pointer to this gray space over here. And this explains to a large extent why it's a really bad idea in a C program to go out of bounds in terms of the space that Malloc has granted you. That you see here, I call Malloc and eventually get a block of 16 bytes back. This is the pointer I have, for instance, the stack. That's to 4 integers. That's what 16 bytes could accommodate in terms of 4-byte integers. And immediately adjacent to that, both preceding it and after it, are important data that is used by Malloc to maintain what's in use and what's available and its ability to sort of traverse that set of stuff. Now, for instance, if I were to overwrite or go off the end of this array, I'd clobber this size that's in the footer over here. The size mirrors the 16 that's in the header down over here. And the footers generally are a little bit smaller. They just have a single size field over here. But getting rid of this thing means that I'll be in trouble later on as other operations are attempted to be performed on this. If I could go too far, like blow through this footer as well, chances are likely that I'll encounter another header that's over here. And if you go way out of bounds on the array, you'll overwrite pointers over here, change this thing not to a U or an A, but to something else entirely in that respect. So importantly, this picture and the overlay of these little bookkeeping data structures explains why going out of bounds in heap allocated memory tends to lead to problems later on, that you screw up the heap and will likely get segmentation faults at some point later on in the program. It also explains, though, why you can go out of bounds and not get any memory errors as a part for the course. Valgrind will oftentimes put these blocks like with a little bit of a boundary in between them and check on memory references to see if you're staying in bounds there. This slows things down tremendously, which is why when you run programs under Valgrind, they go a lot slower. For now, though, we're interested in just a few semantics about how you go forwards and backwards. You'll notice, again, here are two blocks that are adjacent to each other. One's in use and the other is available. Rather, the gray one over here is in use and the yellow one over here is available. This little bit of space in between the header and the footer is arbitrarily big and comes from, if I malloc 64 bytes, then I expect probably there'll be 64 bytes in the block over here. Malloc 16 bytes and we'll get something that looks like this instead. So there's an arbitrary amount of space between these two, which means you'll need some means of navigating. There are two notions of like blocks that are next to each other. Certainly there's the linked list notion, as in this is an available block, so you'd maybe go backwards to say, let me find the previous available list, or forwards to find the next available list. On the other hand, you may want to see what's the block that's immediately adjacent to me in the heap. I'll refer to this not as next and previous, but above and below. So if I have a pointer to this block here, its header rather, and I want to know what's the block above me, which is over here by this in-use block. You can calculate this because you know how big this gap is, and these are fixed size structures. The size of a header plus 16 bytes in this case, plus the size of a footer will get me through pointer arithmetic to the block that's immediately above. Importantly, you can go in the other direction too, that if I have a pointer here to this above block here, I can just do a little pointer arithmetic to say, let me peek at this head down here. And I'll find the 16 bytes that are in here will tell me how big this gap is. So if I take the size of a footer minus the 16 that I find here, minus the size of a head, I can get to the block below me, or at least a pointer to its header down here. This will become important as you navigate around, as at various times you'll need to split off blocks from one another, you'll need to merge them, and the first part of the project is to implement a few functions that are basic access to manipulate and find blocks that are relevant to one another. So for instance, there are 4 functions here that, given a header, find this footer. And that can be done by adding on the size of a footer plus the 16 bytes, or size of a header rather, plus the 16 bytes to get you a footer. And conversely, if you have a pointer to a footer, to find the associated head, that's whatever this number is, subtract that off the location of this pointer to the footer, subtract again the size of the header off, and you're down here then to the associated head. That's that get footer and get header. Okay, remember, one of these is provided to you, and the other is required. Just be careful because you need slightly different techniques in each of them. So as you're looking at one for inspiration, the other one might twist things just a little bit differently. And as alluded to, there is also a set of functions that allow you to say, given this block, which is yellow and has a blue and green part, find this other block up here, that's one above it, or similarly, given the gray block, find the one that's below it. So again, the block encompasses the header, the little space in between, and the footer. That's what's referred to as a block, and they always come as a package. A head, some space in between, and a foot in that respect. The user themselves will only use this space in between if they're behaving as the bookkeeping information is oftentimes referred to as overhead. every time you grant the user some piece of memory to be used that's in between, it's got to be bounded on the front and the back by one of these headers and one of these footers in order to keep track of things there. All right, we're in a position then to understand some of the larger portions of this then. There is a notion then of lists of blocks that track those that are available and those that are in use. And then a global control for structure referred to as L control. The L control T type is associated with this, but there's also a global variable named L control. That's the sort of singular global variable that's allocated early on, to sort of account for where everything is. And initially, the entire heap is one big yellow available block that's based on whatever the total number of bytes in the heap is. To that end, then, the allocation scheme works something like the following. So as you would want to allocate a block, you'll search through the available list and say, let me first find some block that has enough bytes in it to satisfy my request. In the example diagram down here, it's 60 bytes. Now in this case, I found one that's quite a bit bigger than that, 300 bytes. And it wouldn't do to say, here, take the whole block for your 60 byte request, because that's kind of overkill. And to save space then, you'll take this block and divide it into two. The 60 byte part that will be granted as part of the malloc, and whatever remains will be shuffled into a freshly created block that has the remainder blocks. Remainder bytes in it, rather, 200 in this case. Now the math might at first seem a little bit off, is that if I've got 300 bytes and I am going to peel off 60 bytes, I should have 240 that remain. But the careful observer will see, oh, I can't just do the 60 bytes part. I actually need to include a new footer and a new header that wasn't present over here. And to that end, this is referred to again as the overhead, that every time I would create a new block by subdivision like this, then you lose some bytes to the bookkeeping. 40 bytes is a pretty big overhead. It's not so bad for a student project, but in a real implementation of malloc, you'd probably pare this down somewhat, and there's no need for doubly linked lists or two lists for things, and so you could decrease the size of this to maybe a couple words of memory, 16 bytes or so. But we'll make use of larger overhead in this case to make our job in debugging easier. So that's what happens to the extra 40 bytes. So I had 300, I'm going to peel off 60, but I need to introduce 40 more bytes for this foot plus head in the middle, and that leaves me with 200 bytes remaining. And you'll notice then that the first part of this original block, it's separated out and shuffled into the used list. I can return a pointer to the user to say, hey, here's your little 60 byte space, stay in bounds because I don't want you to mess up this other stuff. The original header up here is transformed from an available to a used header. And this freshly introduced block over here is marked as available, and it's now at the very front, the beginning of this available list. Up over here is mention of a function that's important that a number of students have already asked about early in the project release that bears just a little bit of discussion. It is the split block function. Its responsibility is to analyze a given block and determine whether or not it should be split. So given this block here and the request to say, hey, split this, and I want whatever the smaller block is to be, or the sort of new block, one of the blocks to be 60 bytes. The result of this function is shown below, wherein it will take the 300 byte block, it'll partition it off, create a new foot and a new head over here, and say, here's the 60 byte one that was originally pointed to. It's altered. And I'll return a pointer to this 200 byte block that's in the middle over here that I've created. Now, the A's over here are somewhat arbitrary because this is going to be used in the context of an L-malloc, where you immediately take this first one, change it to in use by inserting it into the used list, take the second one, and insert it into the available list over here. On the other hand, someone asks for 60 bytes, and you find one, hey, 80 bytes. That's certainly big enough for the 60 byte business. However, it is not big enough to split because it's less than, in this case, the request size, 60, plus the overhead, 40. So it's less than 100 bytes, not big enough to split. So in that case, we'll take this 80 bytes and just say, nope, this is it. not going to change the size. It's big enough as is. And I'm going to return null from this split function to indicate I can't actually split it. There's no second block over here. So this one just changes, in this case, from available to used, gets taken out of that list and put into the other list. And there's nothing to insert, no additional leftover space. This is just a little bit bigger than what the user had wanted, but no matter. We can't split it any further based on what we have here. Hopefully, with a little thought and consideration, this can sort of become clear to folks, but I'll digress and certainly ask questions on Piazza and in office hours as they come up. Now, going in the reverse direction, this has been allocation so far, and explains why, like, over time, you get this sort of fragmented look over here of like, okay, I'd have a yellow block that spans this entire thing, then I get a little gray block at the beginning and a bunch of yellow, and then another gray block at the beginning and a bunch of yellow. I keep splitting things off. But it doesn't explain this intermingling of gray, yellow, gray, yellow, gray, yellow. That's only possible if you start freeing things. And so down here, towards the end of the spec, is a discussion of freeing things. And there are several cases to consider here. For instance, here's a situation in which a bunch of blocks have been allocated, and the user is pointing at this block over here and says they want it freed. Now, importantly, user is going to sort of say, hey, free this middle block right here, and I have a pointer to it. But the first step in this is to back up a little, to say, oh, I'm not going to work with the pointer the user handed to me. That doesn't point to anything except user data. I need to do a little pointer arithmetic, back up so that I work with its head instead. It gives you access to the size, the linked list nodes, etc. In this case, the freeing is relatively easy. It's like, oh, pull this thing out of the used list and put it into the available list, changing state accordingly with it. And so this thing is now available to grant further cases of Mallocs that might request something like 60 bytes or 50 bytes or 40 bytes, etc. However, there are a few other cases to consider that are based on the blocks that are above and below this thing. For instance, here's a situation in which the user says, free up this 60 bytes, I'm done with it. And as you do so and find, oh, actually the block below me, that's also available. And this is the spot where you'd unsplit things, you'd merge them. And this is to recoup the size of this header in the middle. Instead of having too little available blocks, which wouldn't allow me to sort of grant a request for 150 bytes, instead I would merge them and say, let's just cut out this part over here. And so one of the functions that you'll have to write is to poke around to say, attempt to merge a couple blocks together. If they're both available, then cut out the middle header between them and account for then the recovery of that overhead. So in this case, it'd be 90 bytes plus the 60 bytes that's being freed, plus this header and footer collection over here, the block overhead that can be recouped. So now I've got a 190 byte block over here. And if someone made a Malloc request for 190 bytes, I could satisfy it with this big bugger over here. Hopefully this is making sense to folks. So there are several other cases that you want to examine in this. For instance, the block that's being freed up, the block below it is not available, but the block above is available. So you'd merge those two instead. And finally, the case where both the above and below are available. If you're clever about this, you'll make use of the single function that you're required to implement in this case, which is merge block, merge block with above. And that can be accomplished just with some pointer arithmetic. In this case, if I'm freeing this block over here, find the block below it and say call merge with above on it, and your job will be done. And in the case that you merge several times, it's like merge this one and then merge it with the one above it potentially, and you're good to go. Be very careful that you aggressively merge. So anytime you free, try to merge with those things around you, because that will mean you only need to look at a limited number of cases. There's no iteration or recursion or anything that has to happen here. You're at most going to say, this thing that I am freeing here merges with the one below and the one above, but everything else should be as big as possible in terms of that stuff. The final step in this is to potentially expand the heap. This requires some knowledge of what we're discussing in the lecture right now, the virtual memory system, and in particular the mmap function. you can get a fair amount of inspiration for how you can expand the heap by examining the initial heap setup that is in the provided linit function. I'm going to zip over to that, which is in the code pack. So again, you'll be editing this lmalloc.c function here. If I open that up, the very first function you'll see here is linit. They also notice here that lcontrol, the global variable that pertains to all of the linked list structures and so forth, and how many bytes are in the heap and stuff like that, that's present right at the top. It's initialized to null, but it's the very first thing that linit sets up. Since I'm implementing my own malloc, it wouldn't be fair to call malloc or something like that. So instead, I'll just say, hey, operating system, memory map some space in for me. You'll notice the options down over here indicate I both want to read and write this stuff. I need to give some size associated with it, this L page bytes over here. And these options that are present down here are a little bit different than what we have dealt with in class, where we were attempting to memory map files. Instead, map private and map anonymous mean, hey OS, I don't need this page of memory you're mapping to be associated with any particular file, and I don't need to share it with anybody. This is my own personal private heap, and so go ahead and map it private and anonymous, not associated with the file, and no other programs can look at it. -1 here is an indication that, again, not associated with any file, and there's a specific address for testing purposes that we'll place this at to make this a little bit more sane. Now that isn't the heap itself, it's instead space for the control structure. The heap itself is gotten by a very similar mmap over here that involves the use of this initial heap size over here, which is 1 page of memory if you look at the headers. We then proceed with some setup where we'll say like, oh, the heap starts at this heap location that was granted via an mmap, and the initial size of it is however much I plopped over here. That means then the heap should end. The address first address that should be out of bounds is wherever it starts plus however big it is. And this pointer plus bytes macro is super useful. Allows you to pass in some pointer of an arbitrary type and add on some quantity to it to get a new void pointer associated with it. We're going to be dealing with a lot of void pointers in this. So make liberal use of this macro as you'd want to do pointer arithmetic so you don't get burned by the compiler automatically scaling those pointer arithmetic operations by the size of whatever it is you're pointing at. Now, the reason we're looking here is at heap expansion, and that as you would want to expand the heap, the arguments to that function are how many more pages do you want to add on. You'll notice a couple things over here as I memory map the first part of the heap here. I said I want, if possible, the operating system to place this at a specific address. This lheap start address, that's specified in the header file. And it's always, again, a fixed spot. It starts with this 612 in honor of the zip code, or not the zip code, the area code for dialing a Minneapolis phone number. At any rate, this is to be placed here. And if you want to add on to the heap, the logical spot to start adding pages is at this address, heap end. And so as you'd implement this heap expansion thing, keep in mind that rather than pass in the same address here, you'll actually say, map some more pages, start them at the end of my current heap. You'll want to check that that succeeds, and keep in mind if mmap fails, for instance, you ask too many pages, or there's something blocking mmap from allocating spots at a requested address over here, then it will return some special return values. You can also check to see, hey, did this thing return the address that I requested in terms of the starting address over here. But supposing you get your heap end back, then it's just a matter of like scooching the new heap end to be some size back. And the size that you want to pass in is probably the number of pages times however many bytes are in a page. There's a constant for that as well, but I could forgive you if you use 4096 as well, which is a typical 4K page size that's used on most systems. That's defined over here as well as the size of pages that we'll use for this exercise. With just a little bit more bookkeeping to say the total size of the heap has increased, you'll have allocated a new chunk of memory. And visually, you can just think of that as up here where we had our global view of this thing. This is my initial 1 page of memory, and this is the out-of-bounds address for the heap end. But if I say, hey, OS, map some more space here, then suddenly I've got a new chunk of space over here I can use. Add in a new available block for this, potentially merge with this available one that's below it, and voila, you've got a bigger heap space that could be used to grant mallocs that might have failed earlier. Now, all that is done independent of any malloc or free call, so the idea here that's demonstrated in the demo is that if you malloc can't find an available block that has 150 bytes in it, that would be the case here, then lmalloc returns null. And in our case, you could say expand the heap by 2 or 3 pages. That would append some space over here, and then I could start to make use of this much larger now available block that's the end of it. A lot of that stuff is demonstrated in the LDemo provided code over here, which shows the use case for a lot of this stuff. That initially I have to set up the heap, but then I can run lmalloc in order to get pointers to various spots. And this print stats business will print out some rendition of what the heap looks like. And I can turn your attention to the demo that's provided along with the output that's in here. That's in the spec. The demo program is here. This will do things like, oh, if I allocate, my initial setup for the heap is here. There's just one single block. It starts at the 612 address and is the entirety of the heap. It's 4,096 blocks, but you'll see the size of this, 4,096 blocks in the heap. However, say a total bytes 4,096. However, the total size of this block is only 4,056 because it has a header and a footer that are appending it. So there's no, so that's where the 40 bytes is lost. This little total figure here adds on that overhead and converts to hex, so it makes it a little easier as you're traversing blocks. Now, if I allocate 3 times down here in the demo, you can see the available and the used list have changed. I still have 1 big block of available space left, but there are these 3 little blocks that are in the used list. They all have the state U and are at the addresses 612.0.0.0.0 right at the beginning of the heap, then a little bit higher than that, A8, and then a little bit higher than that, 100. This is the used list, and since each one that's peeled off appears at the head of the list, this is sort of in the reverse order that I malloced them. However, if you actually look at the linear rendition of the heap blocks, you'll see over here, right at the beginning of the heap, this is no longer a big honking available one. It's an in-use block. It has a size of 128 bytes. And if I look over at my demo program, that's the very first malloc that's over here. The next malloc is 48 bytes. And you can see sequentially, I go forwards to address OX A8. That's over here from 00 to A8. And right there is this next block, 48 bytes big, just as I malloced it. And then after that, sequentially, there's a block of 156 bytes. Again, beyond that by a ways. The ending block is the one that encompasses the entire available space that's still there. So there's a great amount of utility to understanding like the semantics of the stuff and how to behave both in terms of the linked lists and the linear layout of how the heap looks as you would go from low addresses to high addresses in the heap in terms of understanding how you might implement or at least the intended behavior overall of these functions. The testing is a little bit, it has more of an integration testing feel where individual functions aren't tested particularly well. You have to implement whole chunks of the code before you can test this stuff because basically these are testing if can I call lmalloc and get some stuff out and then call lfree and it returns the state of the stuff here. Lmalloc and lfree involves the implementation of a bunch of functions in here and the overall structure is given here. For instance, those initial functions to get headers and footers and blocks above and below. There's some required functions to add and remove blocks from the lists that are present there, and some required functions to lead up to lmalloc to find available blocks to split them, and some required to support lfree, notably this merging function. So that is the project in a nutshell. It will reveal many of the mysteries of how the C memory allocation system works, maybe not in its entirety, but explains things like why going out of bounds in pointers or in arrays is no good, why once you allocate the size of an array, it's more or less fixed because blocks around it may occupy stuff that you've allocated later, and you can't easily expand. However, there is a sort of add-on to this to reallocate things to leverage the underlying memory system to potentially expand the size of a block if there's nearby space available. I'll digress at this point and wish you all luck. As you have questions, plop them up on Piazza or come by office hours to talk to us. Happy hacking all, and I'll see you next time in lecture.